So in this recording, we're going to put together things that we've learned about enthalpy and entropy and look at an overall reaction and what we call the Gibbs free energy, which we can use to determine if a reaction is going to be spontaneous at a given temperature. So the second law of thermodynamics says that the total entropy of the universe is always increasing. And when we talk about whether a process is spontaneous, we're asking, is it thermodynamically favored at a given temperature? So we have to combine ideas of enthalpy, which is bond energy, with entropy, which always has to be increasing. So this thermodynamic function is related to something that we call free energy, which has the symbol G. And what we really care about, like usual, is not G, but delta G, or the change in G. So if delta G is negative, it means that the process is going to be thermodynamically favored. And if it's positive, it will not be favored at a given temperature. So G is related to enthalpy and entropy and temperature using this equation, G equals H minus T delta S. And again, we don't care about the absolute values. What we really care about is the change. So this is the equation that we are going to use all the time. And it says that delta G, which is the change in energy, Gibbs free energy, is equal to the change in enthalpy minus the temperature times the change in entropy, and the temperature is always going to be in Kelvin. So we are going to use thermodynamic data to calculate delta G using this equation and then figure out if a process is spontaneous or not. So for the following reaction, nitrogen dioxide dimerizes or combines to make N2O4. Is this process spontaneous? We have delta H is negative 58 kilojoules. Delta S is negative 176.6. And delta S is typically in joules, so we're going to have to convert this in order to use it because they have to match. So calculate delta G at 298 Kelvin. We have to be given a temperature. Is this spontaneous at this temperature? So again, the first thing that we're going to do is to take our delta S, which is in joules, and convert it to kilojoules. So minus 176.6, we're going to divide by 1,000 and change that to kilojoules. Again, it's per degree Kelvin. So using our equation, delta G equals delta H minus T times delta S. Delta H is minus 58. And then we're going to subtract the temperature times delta S. Be careful with signs here because this is going to give us a negative T delta S. But then we are going to subtract that number. So we're going to add them together. And then the overall delta G is minus 5.58 kilojoules. So that is spontaneous because it is negative at 298 K. So at what temperature does it go from spontaneous to non-spontaneous? And we can calculate that by plugging in a 0 for delta G. So at what temperature is delta G going to be 0? Because that's where it goes from positive to negative. So we'll plug in a 0 here and calculate temperature. So using the same equation, whenever it asks what temperature it goes from positive to negative, that's going to be the temperature where delta G is 0. Plug in a 0 here, solve for T, The delta H is the same. The delta S is the same. It's still in kilojoules. And solving for T here, we get temperature is 330 K. Remember, temperature is always going to be in K. If we wanted to convert it to Celsius, subtract 273, and that's going to be 107 degrees Celsius. So this is the temperature where it, below this temperature it is spontaneous, and then at higher temperatures it's not spontaneous. And that's because the entropy becomes so important at higher temperatures. So because this process has a negative entropy change, if we increase the temperature, it's not going to happen, because it's going to be more important for it to have 2 moles of a gas. Okay, so we're going to do the same thing with number 2. Diamond is forever, which was a successful advertising slogan for diamonds, probably in the 80s, 70s, and 80s. But is it true? Is the process carbon diamond converting to graphite? We know it's delta H. We calculated it earlier, and it's negative 1.895 kilojoules. We also know it's delta S, and that's going to be positive because the diamond is highly organized and graphite is less organized. So that's a positive entropy change. But what's the delta G for this process? So again, just like before, we need to convert our entropy in joules to kilojoules so that everything will match. And we're going to use the same equation, delta G equals delta H minus T delta S. For temperature, it's going to be in Kelvin, which is 298 Kelvin, which is given, and solve for delta G. Be really careful with signs. So delta G is minus 2.91 kilojoules, which is, because it's negative, it means that this process is favored thermodynamically. So therefore, diamond is not forever. However, it doesn't tell you that it's fast. This process will take millions of years. So yes, it's favored, but no, it's not quick. Okay, so for number 3, we have a little bit more work to do. We're given the reaction, and that is silver oxide decomposing to make silver and oxygen. Instead of being given the delta H and the delta S, we have to calculate it using the data. So we're going to use Hess's law to calculate delta H, and our delta S equation to calculate this, and then we're going to put them together and get delta G. So it's a little bit more work here. So to calculate delta H, just like we did before, it's going to be the sum of the delta H's of all the products minus the sum of the delta H's of all the reactants. It's going to be 4 times 0 plus 0, which is going to all add up to be 0, minus 2 times negative 30. Be careful with signs. This is overall going to be positive, so it's plus 61.14 kilojoules. Calculate delta S, again using our delta S equation, the sum of all the entropies of the products minus the sum of the entropies of the reactants. This is going to be 4 times 42 plus 205. Add all those together. Those are the products. Minus 2 times 121.7. And overall, that's going to give us a positive 131.7. So that's going to be delta S in joules, because we are given the entropy data in joules. And again, just like before, we're going to take our joules and convert them to kilojoules in order to use it in our delta G equation. So divide by 1,000 to get kilojoules. Put it all together to calculate delta G. At 298 Kelvin, and we get delta G is positive 21.9. Because it is positive, it is not spontaneous at this temperature.